Okay, so week two, we're here for a Physics 116 review. That's General Physics 2, primarily electricity and magnetism, but there were some thrown in topics that are sort of reasonably important. But to the extent that you learn them in class, like for instance, equilibrium, which is quite straightforwardly the fact that F net equals zero and torque net equals zero. That's the definition of equilibrium, and so you can do problems like how do you balance things, and like where if you had a meter stick with a, I don't know. Oh, I guess whatever. Yeah, like a rod with mass m2, and you hang from it a mass m1, and where would that system balance, for instance? Not in its center, right? Somewhere closer over here somewhere. Um, and that's equilibrium. Gravitation, and the beauty of gravitation is, well, first of all, it's just more about Newton's laws and energy conservation, but it also is a good introduction to electricity and magnetism because it brings up the inverse square law, right? Newton's law of gravitation. The gravitational force between any two masses, m1 and m2, is proportional to each of the masses and inversely proportional to their center's distance squared. So if that's r, that's m1 and that's m2. And the, whoops, I did that wrong. It's the minus r hat direction, right? So if m1 exerts a force on m2, m1 on m2 is attracted to m1. So the gravitational force F1 on 2 is in that direction. So if we're talking about the force due to m1, this is the radial direction of m1, and the force is in the opposite of the radial direction, so minus r hat. Okay, so you need to understand that. But anyway, gravitation, inverse square law, force is proportional to each of the masses, inversely proportional to the distance squared, and the proportionality constant is g. We discussed, when we talked about gravitation, also the potential energy due to gravity, which is gm1, or the potential energy due to the gravitational force between two masses. So the potential energy of two masses in the vicinity of each other is gm1 m2 over r. It's a positive potential energy, where that's the potential energy at a position r, and that is defined relative. Remember, whenever you define a potential energy, you always define that potential energy relative to a zero, and that is defined relative, excuse me, that is defined relative to u at infinity equal to zero. So rather than, like when we did gravitation near the surface of the Earth, generally we define u equals zero at the lowest point of the problem. When we're talking about Newton's law of gravitation, we define a very different zero. We define zero infinitely far away. And the potential energy increases from zero as the two masses get closer and closer together. It's zero when they're infinitely far away. Then Physics 116, we do a little bit of fluids. We define density, but then most things don't change from there. It's just an application of Newton's second law and energy conservation, and you get things like, well, density, of course, is mass per unit volume, unless we're talking about some areal density or linear density, but in fluids, we generally talk about volume density, mass per unit volume, and we talk about buoyant force, for example, the buoyant force, which is the force due to submersion in a fluid, and that's due to the fact that the pressure as you go down in a fluid increases with depth h. So if we've got a fluid and we start at the top, this is h equals 0. As we go in that direction into the fluid, if we put an object in the fluid, like a marble, it is going to have, it's going to feel a pressure that's bigger as you go down. P0 is the pressure at the top. In this case, if this is just a cup of water, that would be the pressure due to the atmosphere. And then there's the additional pressure due to the fluid on top of it. So this is the pressure due to the atmosphere, and this is the additional pressure due to the fluid above it. Because pressure increases as you go down, the pressure at the top of this object is going to be different than the pressure on the bottom of this object. There's going to be a difference. And it's that, the fact that P upwards and on top P downwards, right? The fact that the upwards force on the bottom has to be bigger than the downwards force on the top because of this gives you a net upwards force, and that's your buoyant force. And of course it was, what's his name? Eureka guy. Eureka, not Hero. Who was it? I had to look it up to make sure. I tend to forget some of these things sometimes. Archimedes, who was also able to show that the buoyant force, which we could just calculate from this pressure, but the buoyant force is equal to the weight, it turns out from the calculation, the weight of the fluid displaced by an object, submerged in that fluid. So there is a buoyant force on you and me because we're in the atmosphere. Simply because we're in the atmosphere, there is a net upward force on us. We don't float because our weight is greater than that buoyant force, right? So then you can talk about why does something float versus why does something sink, and that's just when you just compare the weight to the buoyant force. So if you've got an object which is in a pool of water, or you submerge an object in a pool of water, let's take a magic box or something, and we say, okay, well, it's got to have a buoyant force upwards, and I'm spelling buoyant wrong somewhere, and it's got a weight downwards, and if the weight is bigger than the buoyant force, then it sinks, and if the weight is smaller than the buoyant force, then it floats, right? And what's an example of something that floats? That's a cork in water. I don't know, I'm trying to think. Wood, at least less dense wood in water. A balloon in air, right, floats. The buoyant force is greater than the gravitational force. And you might remember that it turns out if you apply this definition and you do some analysis, you find out, it has to do with density. If the density of the object is bigger than the density of the fluid around it, then it sinks. If the density of the object is less than the density of the fluid around it, then it floats. And then we did a little bit of oscillations and waves. Oscillations and waves. Certainly important to know things like wave properties, like wavelength, period, frequency, amplitude, angular frequency. And that's different than angular velocity that comes up in rotational motion. I guess what comes up in 251 also is wave number. That kind of covers it for the variables that describe oscillations and waves. And just knows the basics about oscillations and waves. Frequency of oscillation of a mass on a spring, for example, or the fact that a wave carries energy but doesn't carry mass, right? A wave is a disturbance that propagates through a medium. This is just some pretty basic stuff that we did with oscillations and waves. But the important stuff in Physics 116 is electricity and magnetism. So I want to spend time today reviewing a little bit more detail, electricity and magnetism, and the topics that we learned in electricity and magnetism. So that comes next.